Right, so I'm going to talk about anomalies. So we've been searching the skies for quite some time now, and suppose that one day we find intelligent life on a planet far, far away. Wouldn't that be wonderful? Now, this is an anomaly, a very interesting anomaly, also might be slightly scary. But we really want to know about this anomaly. We want to know what kind of life forms would there be on this planet? What kind of technology would they be using? Are they using maths and stats? Are they using data science? What about, do they have computers? All kinds of questions we'd be interested in knowing, right? So that's the interesting thing about anomalies. They are telling a different story from the norm. Look at credit card fraud amongst billions and billions of legitimate transactions. That's of course that's not maybe a nice story as the aliens, but nevertheless talking about a different story. Astronomical anomalies like solar flares and computer networks. You've got lots of people browsing the net, saying hello to other people, and then there's a cyber attack going on. Weather anomalies like tsunamis. So there are many anomalies in different application spaces, all telling a very interesting story. So the question is everything already done in anomaly detection? Well, not quite. There are many challenges. One challenge is the high dimensionality of data. So when data is really, really high dimensional, anomalies look like other points and it's difficult to detect them. The curse of high dimensionality kicks in. And sometimes then the parameter estimation is another issue. So anomaly detection algorithms you've got to specify parameters. And the people who are the end users who are specifying the parameters are not statisticians, not computer scientists. These are people who are far away from that area. And we expect them to specify the correct parameters for the algorithms to work. And then we've got high false positives. So think of an alarm system that you've got in your home. And if the alarm goes off every night at 2 a.m., your confidence in the system quickly goes down. So you need to trade off these high false positives, but not miss the real anomalies. So there's this fine balance between false positives and false negatives. And what kind of features from the data can you extract to make the anomaly detection task really good? And of course, there's complex data types, spatiotemporal data, network data, which takes it into a total different domain. So um, so I'm going to, so this work that I did with Rob Heinemann, in this one, we're looking at dimension reduction techniques, but specially catered for anomaly detection. So what we're using is the k-nearest neighbor distances, which is used a lot in anomaly detection. And we're finding a set of basis vectors in a way that the first basis vector is in the direction of maximum k-nearest neighbor distances. The second basis vector is in the direction of the second highest k-ended distance, but orthogonal to the first basis. So we find this orthogonal basis vectors. The idea is that you can use this basis and use a smaller set of basis vectors and still find the anomalies in that reduced dimensional space. And this other one, this is also with Rob, it's a preprint, and this is talking about this parameter selection issue. That is, people use kernel density estimates to find anomalies, and kernel density estimates require a bandwidth parameter. And, but then generally the bandwidth needs to be specified. So in this work, we used topological data analysis, persistent homology. And I have to say, I learned persistent homology from Kate Turner at AMSI Summer School in 2018. Thanks, Kate. So we used persistent homology to automatically find the bandwidth, and this bandwidth is used in the kernel density estimate and then later used in extreme value theory and used for outlier detection. So that so that the end user doesn't need to specify the bandwidth. Then Another thing is you have lots of anomaly detection or outlier detection algorithms, and you have different types of problems. How do you do this matchmaking? Because there's no unique algorithm that's always best for all problems. So you need to kind of match. This algorithm goes better with this problem, with strengths and weaknesses. So this is work mainly with Kate and the team, Kate Smith-Miles and the team, that is looking at instance space analysis, which is research area that Kate has been doing, and looking at how do you do this matchmaking. And also we found out in the way that the normalization technique really, really matters. So that led to some other work with Kate. That is, can you? We looked at item response theory. That is generally used for in educational psychometrics. And what that does is it looks at test questions and participants taking test questions like that. And then, it looks at questions and says, this question is very discriminative. This question is difficult. So it analyzes the question. So can we use that for evaluating a portfolio of algorithms? So we use different mapping, and we could evaluate a portfolio of algorithms. And in this example, we have this latent trait, and here it would say these are very difficult problems, and this particular algorithm C is best for the very difficult problems. These are very easy problems, and the algorithm A would be better for easy problems, and for the middle problems, algorithm D is suited for like the middle of the range problems. So mapping item response theory to that. And then moving on, so then I was thinking, oh, can we use item response theory to make an anomaly detection ensemble, this latent trait that item response theory gives us? Because in anomaly detection, we don't generally have the class labels. It's mostly unsupervised. So can we have use item response theory to do that? And in this example, these anomalies, the blue dots, are moving away from this set of points into the middle, and we have several ensemble methods, and the anomaly, the IRT based methods, is a better ensemble because it's using this latent trait to come up to find the hidden labels. And currently I'm working on different things, and one of the things that I'm doing with Asha and Hidea is these computer network attacks and computer network anomalies. And finding these computer networks in cybersecurity. And then that leads into anomalies and events in when you have a network, like a graph, and how would you, the rich mathematical frameworks and things that are available for graphs, how do we use that to find anomalies? And then, of course, the spatiotemporal data and events. And I'm also interested in sensor data applications, because these are really interesting and, in a way, challenging data for different reasons. So that's my current work, and thank you very much for listening.